The next section in Chapter 5 is 5.3. It talks about the fundamental theorem of calculus, and this actually defines the integral. And the integral is also known as the antiderivative, because it's really just the derivative backwards. You find the function who has the given derivative. But what the integral really does is it finds the area under a curve, f of x, from one x point to another x point. So it's really just giving us the area. And the area above the x-axis is always thought of as positive. The area below the x-axis is always thought of as negative area. So we add these together to get a net area. And if you look at the actual integral itself, the integral, that's the integral of f of x dx, represents the antiderivative of f of x, which is the opposite of a derivative. So first we're going to look at this integral as an area under a curve. So I have two integral functions. I have the area of x goes from 0 to x of f of t. That's a of x. F of x goes from 2 to x of f of t. So what a of x represents is start at 2 and go out to x and figure out what the area under the curve is. So a of 2. If I take the number 2 and replace x with it, notice it went from 0 to x. So what's in the parentheses is what we put up here on the top of our integral. That's the integral from 0 to 2 of f of x dx. Now notice all we did was replace the x in there with the number 2 in the parentheses. And what this represents is the area under f of x from x equals 0 to x equals 2. That's really what that represents. And if you look at the graph, here's x equals 0, here's x equals 2, the area under it is 8. So the answer to A is 8, because that's the area under the graph from 0 to 2. B. B is f of 2. So I have to start off with f of x. F of 2 equals, well, notice what f of x did. F of x went from 2 to x, but I'm replacing this x with the number 2. So f of 2 is the integral that goes from 2 to 2 of f of x dx. So that's the area under f of x from x equals 2 to x equals 2. Now this is weird, because the x value is the same on both of them. So if I were to look at the area from x equals 2 to x equals 2, there's nothing but a dot there. There's no area to find because I don't move across the x-axis to have an area be generated. The x value is just 2 in both instances. There's no area under that because it's at a single point. So the answer is 0. Oh, let's look at a of 5. Well, if you look at the function a goes from 0 to x, but I'm replacing my x's with a 5. So a of 5 is the integral from 0 to 5. And that's the area under f of x from x equals 0 to x equals 5. Well, if I look up here at the graph for the area from 0 to 5, from 0 to 2, is a positive 8 because it's above the x-axis. Here is x equals 5. The area from 2 to 5 that's a negative 5 because it's below the x-axis there. So the total area under the graph from 0 to 5 is 8 plus negative 5, which is 3. Notice the area under the x-axis is considered negative. So here the answer is 3 because the area above the x-axis was 8 and below the x-axis was 5. So it becomes 8 minus 5. This is for part C. Part D is f of 5. Well, that's the integral from 2 to x. Remember, f of x goes from 2 to x, but I'm replacing x with the number 5. So this is the area of 2 to 5 of f of x dx. And if I look at the area from 2 to 5, the area is 5. But since it's below the x-axis, it's a negative 5. So the answer is negative 5 for part D. So notice we just have to recognize what the integral is telling us. In A, we have the integral from 0 to 2. That's the area under the curve from 0 to 2. In B, the integral from 2 to 2. That's the area under the curve from x equals 2 to x equals 2. There's no movement there, so there's no area. Part C is the area from x equals 0 to x equals 2, or from x equals 0 to x equals 5. That's what part C is. And when I look at that area, 8 of the area is positive and 5 of the area is negative. So the total area is 3. And in part D, we go from 2 to 5. The area is 5, but since it's below the x-axis, we call it negative 5. So let's look at what an antiderivative really is. This is how we actually calculate an integral without looking at a graph to find the area. Let's say I had the integral of 3x squared dx. That's what that says. And what that means is find the function whose derivative is 3x squared. And I can find a lot of answers. If I take the derivative of x cubed, I get 3x squared. So there's a possible answer. But I could have taken the derivative of x cubed plus 1. The derivative of x cubed is 3x squared. The derivative of 1 is 0, so it wouldn't have shown up. So that's a correct answer. X cubed gives me 3x squared. The 2 would give me 0. So I could take the derivative of x cubed plus 2 and get 3x squared. The derivative of x cubed minus 7 is 3x squared. The derivative of x cubed plus 1/2, 3x squared. The derivative of x cubed minus pi is 3x squared. Because these things I'm changing are constants, and their derivative is 0. So in general, what we do is rewrite x cubed plus c, where this c represents any number that you want to put there. Because when you take the derivative of the c, it goes to 0. The derivative of x cubed gives me 3x squared. So this c is called the constant of integration. And that's what happens when we don't have numbers on the integral. We don't know where to stop or start. If we know where to stop or start, this constant can be determined and we just get an answer. But in this case, we don't know where to start or to stop, so we have to include this constant of integration when we're working through it. So here are the integral properties as well. If you have a constant number multiplied in front of your function, you can factor the constant out of the integral. If you're adding or subtracting two functions inside an integral, you can add the first one, or you can take the first one and add or subtract the second one. So you can separate integrals around plus or minus signs. You can factor numbers out of integrals. And if you have bounds, that's what happens when we put numbers on this integral. This is the integral of f of x from a to b. Well, what this is you can actually get an answer for this, because this represents the area under f of x, this is what we were looking at before, from x equals a to x equals b. Since this is going to give us a total area, we just find the antiderivative. That's what the big capital F means. If I take the derivative of the capital F, I get the little f back. That's what the antiderivative means. But I just plug b into the antiderivative and subtract what I get when I plug a into the antiderivative. This is called a definite integral because you get a number out. You could definitely figure out what the number is. But that's only when there are bounds on the integral. And there's another theorem which we've seen before. Consider the integral of x cubed. What do I take the derivative of to get x cubed? Well, I take x to the fourth over 4. If I take plus c, the integration constant. The derivative of x to the fourth is 4x cubed, and that 4 will cancel the 4 on the bottom. If I take the integral of 1/2, I add 1 to that, I get x to the 3/2 divided by 3/2, which is 2/3 x to the 3/2. The general formula, this is the power rule. It says if you raise x to the power in an integral, add 1 to the power and divide that number, plus c. So notice here the power was 3. I added 1 to the power and divided that number. Here the power was 1/2. So I add 1 to 1/2, that gives me 3/2, which is 1.5. and I divide by that number. Now notice since I divided by 3/2, I multiplied by the reciprocal. But in either case, if you're integrating x to a power, you add 1 to the power and divide by that number. That's the opposite of what we did for the derivative. So let's look at some examples. These ones are some definite integrals. When we're trying to work these out, I'm going to work them out as definite integrals. So what I want to do is find the antiderivative and then plug in the top number minus the bottom number. Well, we know that this integral can be broken up among plus and minus signs. So you could think about this as negative 2 to 3 x squared dx minus negative 2 to 3 x dx minus the integral from negative 2 to 3 of 6 dx. And now we can use the power rule. Now generally people don't do this. They'll just take the integral of each piece inside here and plug it in all at once. So there's a better way to work through this than what we do. So let me not do it this way. What we do really is we just work out the integral from each one of these. So let's see, what is the integral of x squared? Add 1 to the power, you get x cubed. Divide by that number, you get 3. Minus. Let's do the integral of x. That's x to the first power. When I add 1 to that, I get x to the second, and I divide by the number 2. Let's look at the number 6. What do I take the derivative of to get 6? Well, 6x is what I take the derivative of to get 6. You take the derivative of 6x, you just get 6. But the reason why is because 6 is the same thing as 6 times 1, and another way we can write 1 is x to the 0 power. So when I'm integrating this stuff, this is the same thing as 6x to the 1 over 1, which is 6x. So that's why I got a 6x there. But I got to plug my bounds in. So people will usually draw a little line like this. So let's go ahead and plug in these bounds. First I plug in the big bound, or the top number. That's 3 cubed. Hang on, let me put these in a different color. So first I'm going to put in the number 3, wherever the x's are. And then I'm going to subtract from that what I get if I put in the number negative 2, where the x's are. So let's work out what we get. In this first box I get 27 over 3, which is 9. That's 9 over 2, and that's 18. In the second box I get negative 8 over 3. That's minus 4, that's 4 over 2, which is 2, plus 12. So this is, now I'm typing this into the calculator. I get 9 minus 9 over 2 minus 18. The first part is negative 27 over 2 minus. Now the second part is negative 8 thirds minus 2 plus 12. And when I type that in, I get 22 thirds. So I do that in my calculator. I got negative 27 over 2 minus 22 over 3. When I'm all done, I get negative 125 over 6. Or if you wanted to write it as a decimal, negative 20.83. The reason it's negative is because the area of this graph is below the x-axis mostly. There's more area below the x-axis than above the x-axis. And the difference is negative 20.83, because remember, above the x-axis is a positive area, below the x-axis is a negative area. So that's the idea of the antiderivative. You add 1 to the power, divide by that number, and you get the antiderivative. That's what this is. And then you plug in the upper number, the top number first, minus plug in the bottom number second. So let's try it again. Same idea, except now I have x plus the square root of x. Now one of the things you have to learn is when you're doing this, you want to rewrite it so all of your roots show up as powers. And the square root of x is x to the 1/2 power. Now since I can take the integral around plus and minus signs, I can take the integral of each one of these. The first one is x to the first. So I add 1 to the power, x squared, and divide by that number, 2. Plus x to the 1/2. When I add 1 to 1/2, I get 1/2. That's 3/2. But I have to divide by that number. And then my bounds go from 0 to 1, so they usually write a straight line for that. Dividing by 3/2 is the same thing as multiplying by 2/3. So I just rewrote it so it looked a little nicer. But now I can calculate this. First I'm going to plug in 1, and then I'm going to plug in 0. And I'm going to subtract what I get when I plug in 1 minus what I get when I plug in 0. Well, the first one gives me 1/2 plus 2/3 minus, the second one gives me 0. So I type this into the calculator, 1/2 plus 2/3, or I could use my math skills. In either case, I get 7/6, which is 1.1 repeating 6. But either one of those will work. I'll take the fraction, or I'll take the decimal. It does not matter which way you write it. However, in reality, the fraction is usually the easier one to work with. Sorry, my screen is having issues today. Oh, let's try it again. Number 4. Well, the first thing I'm going to do is rewrite this as 2 plus t. Now the square root of t is t to the 1/2. But I haven't put it on top yet. I can simplify this some more. A t to the 1/2 on the bottom is t to the negative 1/2 if I bring it to the top. But now I can distribute this t to the negative 1/2 inside the parentheses. And I get the integral from 4 to 9 of 2t to the negative 1/2 plus, when I multiply these together, I add their powers, and that's t to the first. 1 plus negative 1/2 is positive 1/2. So notice that's what I get when I distribute the t to the negative 1/2 through. 2t to the negative 1/2, t to the positive 1/2. But now I can actually integrate. The first one gives me 2 t to the negative 1/2. I have to add 1 to that. Negative 1/2 plus 1 is positive 1/2, and I have to divide by that number. Now I do the same thing with t to the 1/2. When I add 1 to a half, I get 1/2. That's 3/2, and I divide by that number. This goes from 4 to 9. Well, dividing by 1/2 is like multiplying by 2, so 4t to the 1/2. Dividing by 3/2 is like multiplying by 2/3, from 4 to 9. So I plug in 4 for t, plug in 9 for t, minus, plug in 4 for t. So let me plug in my 9 for t first. Notice the top number gets plugged in first, minus, now I'm going to plug in the bottom number, which is the number 4. And I can put this in my calculator. So I have 9 to the 1/2 is 3 times 4 is 12. Minus 9 to the 3/2, I believe, is 27. Yep. Times 2/3 is 18. So this is 12 minus 18 minus, that's 4 times 2, which is 8, minus 4 to the 3/2 is 8, times 2/3 gives me 16/3. And so I get negative 6 minus 8 minus 16/3. 8/3. And negative 6 minus 8/3 is negative 8.6, which is the same thing as negative 26/3. So in either case, we've figured out the area under the curve, and since it's negative, it means that most of this area is below the x-axis. I think I did something screwy. Let's see. You got, so I'm double checking this integral here to make sure I didn't do anything silly. 4 to 9. This is 2. So let's see, I should get 50/3 if I do this. So let's go back and double check this. That's t to the negative 1/2. I distribute that 2, I get 2t to the negative 1/2 plus t to the positive 1/2. So I take the integral of negative 1/2, I get positive 1/2. If I take the integral of 1/2, I get 3/2. So I have 4 times 9 to the 1/2 minus 2/3 times 9 to the 3/2. And that gives me negative 6. Now I'm going to put 4 in there. I get 4 times 4 to the 1/2 minus 2/3 times 4 to the 3/2. So I get negative 6 minus 8/3. Which is negative 26/3. So it looks like when we're working through this integral, negative 26/3 is what we'll get. Well, I'm going to try another one of these just to double check it to see how it goes. To see what that answer should be. Let's try the cosine of x. So to work this out, I have to figure out what the integral of the cosine of x really is. So to find the integral of the cosine of x, say, what do I take the derivative of to get cosine? The derivative of sine gives me cosine. So when I take the integral of cosine, I get the sine of x from 0 to pi/2. If I take the derivative of sine, cosine comes back, so I know that's the antiderivative. So I just plug in the two values. First I plug in pi/2, then I plug in 0. The sine of pi/2 is 1, the sine of 0 is 0. So the area under that curve is just 1. This last one here, this next one, to work out this integral, it's multiplied together. Those terms aren't expanded all out. So what I'm going to do first is FOIL. I have x minus 4 minus x squared plus 4x. And I can combine like terms. So this is the integral from 1 to 4 of negative x squared plus 5x minus 4. That's what I get when I combine the like terms. But now that I've expanded it all out, I can use the antiderivative. Negative x squared becomes negative x cubed over 3. 5x becomes 5x squared over 2. And 4 becomes 4x. And we're evaluating this from 1 to 4. So first I take this thing and plug in the number 4. Minus, take this thing and plug in the number 1. So first I plug in the number 4 because that's the top one, and then I plug in the number 1 because that's the bottom one. So I calculate this out. I get 4 to the third over 3. That's negative 64 over 3. Plus, I think that's 40. 5 over 2 times 16. That gives me 40. Minus 16. Minus. I get negative 1/3 plus 5/2 minus 4. So we'll type this into the calculator. Negative 64 over 3 plus 40 minus 16. That's 8/3 minus negative 1/3 plus 5/2 minus 4. That's negative 11/6. So I have 8/3 plus 11 over 6, which gives me 4.5 or 9.2. Or 4.5 or 9 over 2. Either one of those is fair. So when you're working these out, you have to expand it so that you're not multiplying anymore inside there. And then when you work it out, after you find the antiderivative, you have to plug in your bounds. It's the upper bound minus the lower bound. So 4.5 we get for number 6. So let's look at the last example in 5.2. This is an example where we can use the properties of integrals to help us. Notice from a to b of f of x is 9, and from a to b of g of x is negative 4. And they want me to find the integral from a to b of 2f of x minus 3g of x. And the tricks that we remember here is we can break up an integral where we add and subtract things. So that's the same thing as 2 times the integral of 2f of x minus the integral of 3g of x. But then I can factor constants out of the integral. So this is the same thing as 2 times the integral of f of x minus 3 times the integral of g of x. But I know what the integral of f of x is. The integral of f of x, they told me, was 9. And the integral of g of x, they told me, was negative 4. So when I work this out, I get 18 plus 12, which is 30. So that integral works out to be 30. Notice I didn't even need to know what f and g were. I could use these properties to move the stuff away till all I had was the integral of f of x and the integral of g of x. That's where I got the 9 and the negative 4 from. We can do that again. The same thing. This is the integral from a to b of 1/4 g of x dx minus the integral from a to b of 2/3 f of x dx. And I can factor the constants out. So I can factor out 1/4. There's integral of g of x minus 2/3 times the integral of f of x. But the integral of g of x is negative 4. And the integral of f of x is 9. Notice I replace this with a negative 4, and I replace that with a 9. So I work this out, and I get negative 1 minus 6, which is negative 7. So the area under that curve is negative 7. So notice, if I'm just giving you functions, you can use these integral properties to simplify it, and then you can find the area.